Welcome. Today I'm going to talk about high-performance computing and artificial intelligence workloads in Rancher. I am Terry Smith, the Global Partner Solutions Director here at SUSE. We have a number of items on the agenda today, so let's get started. Both high-performance computing and artificial intelligence are in the domain of scientific computing, a field of computer science focused on using advanced computing capabilities to solve complex problems. Both HPC and AI are performance-driven. They make heavy use of parallelization. Both rely heavily on access to data. And replicability is essential in science and deep concern for HPC and AI. And interestingly, they are both largely open source and have rich development communities through which they leverage the power of many. In HPC and AI discussions, we often give a lot of attention to hardware, which is important. But it's the software where we make things happen. HPC and AI would not be possible without heavy use of parallelization to speed up computations. Here, we illustrate how a complex problem can be broken into smaller, independent tasks that can be solved in parallel, resulting in faster time to result. The key here is to know the dependencies between the different parts of the problem. In this illustration, green tasks 1, 2, and 3 are independent of each other and can be solved in parallel, say on separate processors. But while blue tasks 4 and 5 are independent of each other, they rely on the results of green tasks 1 and 3, and so must wait for their completion before they can be performed. A similar dependency exists for orange tasks 6, 7, and 8. Still, by carefully understanding these dependencies and utilizing parallelism correctly, we have been able to get our result much faster. The previous illustration is known as task parallelism, where complex problems are broken into simpler ones that can be worked on independently. A few other approaches to parallelism include data parallelism, which focuses on splitting data into independent chunks that can be processed in parallel. Model parallelism, which is most often discussed in the context of artificial intelligence, and it focuses on dividing a model into parts that can be processed separately. Instruction-level parallelism is a type of task parallelism that focuses on doing basic computing operations like load, multiply, and store, all in one clock cycle. This requires the right hardware and compilers that can leverage such hardware. It goes without question, but I'll say it anyway. Parallelization is not easy. High-performance computing is heavily used in the physical sciences and engineering disciplines involving complex calculations such as modeling the collapse of a star, climate change, or a new rocket engine. Computations can be quite complex, highly repetitive, and involve massive amounts of data. It is primarily a distributed parallel computing activity where work is distributed across multiple compute nodes to reduce time to result. HPC application developers spend a significant amount of time determining optimal ways to parallelize how they solve their problems. And they often leverage a wealth of shared libraries that provide optimized routines for common parallel operations. A typical HPC cluster consists of one or more login nodes where users can launch their jobs, one or more head or controller nodes that manage the cluster resources, job scheduling, user access, and so on, many compute nodes where the actual work is performed. Some clusters may offer classes of compute nodes with special hardware like GPUs, large memory, and other features. You can usually find 2 networks or more in a high-performance computing cluster. One is typically used for general management, and another is used for high-speed, low-latency communications. Storage can be handled in a variety of ways, but there's typically a standard storage for user files and data that are not actively being used, and a high-performance parallel storage system that is used for actively running jobs. And let's not forget the most important part of any cluster. It's the user community. They drive what we are doing. High-performance computing developers, administrators, and users face a number of challenges. Some include HPC applications often rely on a complex weave of libraries. These dependencies are often version-specific. Applications and libraries are developed in different cycles by different groups, making it very easy to break an application with just a single update. Most HPC environments are also multi-user, and users often need different applications and different versions of applications, each with its own set of dependencies. It is difficult to package, distribute, install, and replicate such complex software landscapes. This makes replication of experiments, which is essential in science, incredibly difficult. Also, not everyone has access to an HPC cluster. Let's now turn to artificial intelligence. AI covers a broad domain. Here, we're going to focus on a subset of AI known as deep learning, or DL. Deep learning is primarily involved in the use of artificial neural networks, which attempt to emulate the way living brains learn and respond to input. We find application of deep learning in image recognition, natural language processing, autonomous driving, or the modeling of complex systems like biological evolution, the stock market, or the formation of galaxy clusters. We are also just beginning to tap into the power of deep learning to solve various problems. Deep learning focuses on neural networks, so it might be good to have a little understanding of what a neural network is. Neural networks are usually represented as layers of interconnecting neurons. There's typically an input layer, an output layer, and one or more hidden layers in between. Now, real, practical neural networks are far more complex and varied than anything that can be portrayed or in such simple diagrams. And interesting networks may consist of thousands of hidden nodes and involve additional convolutions, feedbacks, and other operations. Neural networks are not programmed like standard software applications. The AI developer actually focuses on programming the structure and the algorithms and functions that define the network or model, but programming happens when the network is trained. Training is accomplished by adjusting the strengths of the connections between these neurons while feeding data, lots of data, into the network. Sometimes training doesn't work or isn't fast enough, so developers may leverage continuous innovation, continuous delivery pipelines to help improve their models, which sets off a pattern of retraining each time. Artificial intelligence uses artificial neural networks, but how are they implemented? Typically, They are implemented as a series of matrices or multidimensional arrays that represent the strengths of the connections between those neurons. Strengths are adjusted through linear algebra operations like matrix multiplication. Now, you probably remember how tedious matrix multiplication can be. Now, imagine doing this with matrices that could involve hundreds of rows and hundreds of columns representing the input parameters. Then repeat this over and over again for tens, hundreds, maybe thousands of layers in the network. And again, thousands, millions, tens of millions of units of data. This is how training is done. It involves a lot of repetitive, tedious matrix arithmetic and lots of data. Fortunately, artificial intelligence communities can leverage the technologies and lessons learned for HPC, such as using optimized parallel algorithms to perform basic linear algebra, offloading these operations to modern hardware like graphical processing units, field programmable gate arrays, and application-specific integrated circuits, using large shared memory to reduce data movement, and using high bandwidth, low latency interconnects to speed data when it is necessary. And also leveraging optimized libraries, toolkits, and frameworks to ensure optimal performance and also simplify development. Doing so does introduce complex software landscapes. So, there are a number of common challenges faced by the AI and HPC communities. First, parallelism is not easy. Software stacks are complex, difficult to install, manage, and replicate. Hardware is often leading edge in complex architectures and limited in availability. And access to data is essential. Let's explore container technologies. First, there are some obvious benefits to containers. They ease distribution by enabling you to easily package everything needed to run your application. They simplify installation by separating the dependencies of one application from another. They minimize environmental differences, making it easier to replicate experiments elsewhere. And they accelerate development by increasing reusability, making it easier to test and share and enable continuous innovation and continuous delivery pipelines. At its simplest, containers are software packaging vehicles. In computing, containers of one form or another have been around for quite some time. They may have been referred to by other names like CH-root jails and virtual machines. But the modern container really came into its own with Docker in 2013 as a lightweight, easier alternative to package software and isolate processes. Docker containers take a layered approach. You begin with a base image downloaded from a registry. Then, in a Docker file, you define a custom image that includes the libraries and applications you need. You only include those things you need, and you get everything else from the host computer that will run your container. And finally, you execute that container on some host. Now, since you just provide or specify a base layer and the instructions to build the application layers, Docker containers are incredibly lightweight. They're easy to share and typically published in a registry for others to download, try, modify, and share further. It is important to note that containers are Linux. So, It should come as no surprise that the Linux Foundation has been heavily involved in developing open standards through the Open Container Initiative and the Cloud Native Computing Foundation. Docker helped launch the modern container revolution. The OCI and CNCF and other organizations have helped define the open standards that have enabled a blossoming of new and powerful capabilities around containers. One of these capabilities is expressed by Kubernetes. Working with a few containers running on a single host is not too difficult, but it quickly becomes unmanageable as containers and hosts multiply. There are other ways to orchestrate containers, but Kubernetes is by far the most common, finding its way into the IT landscapes of many organizations and on nearly every public cloud platform. Kubernetes, or K8s, abstracts many of the details of container management, making Kubernetes an easy way to manage workloads. You can deploy a group of containers called a pod almost anywhere without knowing much about the underlying infrastructure. With Kubernetes, you can enforce policies, ensure resilience, and dynamically scale to meet demand. Kubernetes is open source, and there are many implementations, but those Kubernetes distributions that support required APIs are the only ones that can achieve certification by the Cloud Native Computing Foundation. And the good news is that while there are many Kubernetes distributions, if it is CNCF certified, you can be guaranteed of certain capabilities. One of these capabilities is a standard API called the Container Runtime Interface, or CRI. The CRI enables a Kubernetes cluster to use one or more container runtime daemons like Docker's Containerd, the Kubernetes optimized CRIO, and other options. Let's take a moment to look at the architecture of Kubernetes clusters. They share a lot of similarities with HPC clusters. There are one or more control nodes that manage the cluster. There's worker nodes that perform the work, networking structures to ensure communications, and storage of various types to support workloads. A single Kubernetes cluster is not too difficult to manage, though there are a lot of aspects such as user authentication and security protocols and other capabilities within the cluster that may need to be managed. But it would be nice to have some mechanism to simplify this process. We have this in Rancher. Rancher is an open source Kubernetes management platform from SUSE. Rancher simplifies the provisioning, configuration, and management of robust multi-cluster Kubernetes landscapes on premises, in the cloud, and at the edge. Rancher supports any CNCF certified Kubernetes distribution, including its native Rancher Kubernetes engine, all of the cloud implementations, and even K3s, which is designed for deployment of devices at the edge. Let's take another look at container technologies, and in particular, let's look at Singularity. Singularity is an open source, cross-platform container system developed by researchers at Lawrence Berkeley National Laboratory, specifically for HPC clusters. Singularity uses a single file for container images. So while Singularity image files are typically larger than the lighter weight Docker images, there's no need to go through a layering build process to run them. Image files can also be marked immutable and cryptographically signed. And speaking of security matters, the user running inside the Singularity container is the same user who launched the container. This is unlike Docker, where the user inside is root. In multi-user high-performance computing cluster environments, security is a concern. Singularity addresses this concern. Singularity provides simplified access to resources like GPUs and file systems. It supports data-intensive workloads and message passing interfaces with native support for high-performance networks. And Singularity is integrated into traditional HPC job schedulers like Slurm, Torque, and PBS Pro, which may be more familiar to HPC users and administrators. But what if you don't have access to a traditional HPC cluster? Well, Singularity is fully compliant with the Open Container Initiative's standards, so you can run Singularity containers in a Kubernetes environment. This is enabled by a couple of projects. gRPC is an open source project that enables high-performance remote procedure calls, allowing low latency, highly scalable, distributed applications. It is actively developed and supported by the Cloud Native Computing Foundation. Singularity CRI provides a Singularity Kubernetes container runtime. This project was initiated by Scilabs, who provides commercial support for Singularity today. And while Scilabs has redirected their focus to other projects, Singularity CRI remains open source. So if you're interested in furthering this development, do check it out. Let's take a moment to look at a couple of projects in the open source realm. A Rancher Kubernetes ecosystem simplifies cluster and workload management, but it can still take some effort to set up the complex workflows and pipelines needed for AI. kubeflow is an open source project dedicated to making machine learning workflows on Kubernetes more simple, portable, and scalable. The initial development was around TensorFlow AI framework, but developers are actively extending support to PyTorch, Apache MXNet, and other frameworks and toolkits. Another very interesting open source project is K3 AI. It is a lightweight infrastructure in a box, specifically built to install and configure AI tools and platforms for quick experiment and production on edge devices. This lightweight approach, it is Kubernetes, and it offers an opportunity for developers to create Kubernetes deployable applications with nothing more than a laptop. High-performance computing and artificial intelligence share a lot of commonalities. Key to both is the power of many. Science relies on open collaboration, so it is not surprising that scientific computing is largely open source and driving the development of many new technologies. With container technologies, today's HPC and AI communities can experience simplified packaging and sharing and replicability. Flexibility to use a variety of IT landscapes and architectures on premises, in the cloud, at the edge, and beyond. And accelerated development, testing, and deployment through reusability and sharing. Containers help us leverage the power of many and to innovate everywhere. Thank you so much for joining me today.